So today we are going to discuss about, we start with a core part of Unit 1, that is mathematical modeling. So let us see what is mathematical modeling. Ganesh, over there.
Yes, sir.
So can you see this clearly?
So, for other side, for me, it's stuck.
It's not clearly visible.
For me, it's stuck at the second
Sir, it's visible, but
Oh,
it's
okay, you
stuck,
didn't play
sir.
it. Never mind.
Actually, no, I
Okay.
tried to play online.
It's a video. I thought you were writing it.
One second, hold on. Actually, I thought of making a live demonstration, but it was stuck due to some bandwidth issue. I don't know. So for this class only, whatever was recorded, I am playing again. But from next class onwards, I will try to take it live. I will tackle the issues. But wordings are visible?
Yes, sir. Yes, sir.
Okay. So that is okay. That is fine. So there was one more option to play the recorded video. I'm trying to do with that. So okay, everyone. We start with mathematical modeling of physical systems. So we have discussed what is open loop, closed loop. Then what is single input, single output, what is multi-input, multi-output, and some examples. So now we will start from the most fundamental part of control system. So in this mathematical modeling, we define a mathematical equation for all the physical systems. So the very known mathematical definitions of physical system for you is electrical elements. So we can categorize RLC as a elementary electrical subsystems, you can say. So we can write a mathematical equation for R and L and C. So if I ask you to represent a mathematical equation for resistance, then it is with respect to voltage applied and current flowing through it. So it is from Ohm's law, V equals to I into R. Okay. So how do you arrive at this equation? How do you say V is equal to I into R? Why it is not I is equal to V into R? Okay. Or why it is not V equal to I by R? I am not going for that. I hope it is clear. So everyone knows how V equal to IR has arrived. Then for inductance, similarly, we have V is equal to L di by dt. Okay. So similarly for the capacitance, we write I equal to C dV by dt. Or another definition, V equal to 1 by C integration of I dt. So I written these equations without any integration limits or without adding a function of time, just to avoid the confusion. Okay, I hope it is clear for everyone, and there is lot more things to be done with these equations, which we have already done in your previous course, network analysis or electronic circuits. So now we will jump on to the mechanical elements. So Ganesh, is it visible now?
Yes, sir. Yes, sir.
I'll clarify it again for everyone. I could not run a live video while writing because of some issues, I don't know. But automatically the video was recorded. So I'm playing it again, and only for this session. Please try to adjust, cooperate. I will pause and explain everything clearly. Okay. So whenever I pause, don't feel that your video is getting stuck. Okay. Fine then. So now we'll start with the mechanical elements. We have finished the electrical elements. So late joiners, please understand the left side equation. And we are starting now with the right hand side with mechanical elements. So can anyone tell me the elementary subsystems of a mechanical system that you have come across? Any mechanical system, consider a bike or a bicycle, and how we can arrive or find out the more basic elementary subsystem of a mechanical system. Similar to RLC in electrical, what elements exist in mechanical is the question. Can anyone answer? Just try it out. Okay. So the first and foremost mechanical elementary block we can say is mass. Okay. So the mass is one of the elementary block. Then what is the other one? What might be the other elements? So other element that you can observe in say in bike is
Force.
yeah, force is of course a mechanical signal we can say, but it's not an element. It is
sir.
just like V or I, voltage or current. Force is also kind of a parameter we can say. But when I ask with respect to element, it is a physical element. Fine. So another one you can say is spring, which will be present in shock absorbers. Okay. So that is the another element in any mechanical system. Next, the third one is most commonly known is friction. Friction that exists in mechanical elements or damper. We call it in control system as damper. So just like RLC, we have mass, spring and damper in mechanical system. So let us highlight a little bit on this RLC part, why we call them as a elementary subsystems or most basic components of electrical system is because any complex circuit can be reduced back in terms of RLC. So you might have seen equivalent circuits of say some transistor and all in digital electronics or electronic circuits, that when you write equivalent circuits for say some simplification purpose or some analysis purpose, most commonly we replace with R and C. Okay, any junction in transistor or diode. Okay, or if you even go for a power electronic circuits for analysis purpose, we often reduce back to R or L or C. So we can call them as basic blocks, components or subsystems of electrical. Similar to electrical, in mechanical, if you want to reduce or represent any complex mechanical system in terms of elementary blocks, these are the three in which you can represent. That is mass, spring and friction or damper. So if you take a bike as an example, it will have a mass. Okay. Okay, let us not take a bike, a complete system. Let us take wheel as subsystem. So wheel will have a mass, it will have some friction, it will have some spring in terms of shock absorbers. So that's it. Is there any other element you can find other than this? Okay, so I have not came across other than these three. So I also feel there exist only these three elements in mechanical as elementary blocks. Okay, so next let us move ahead with a mathematical definition of these mechanical elements. Everyone following my explanation? At least I want to answer 10 students, please.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes,
Yeah.
sir.
Okay, fine, that's fine. So initially I'll be a little bit slow because I feel the first part of the first unit is a very basic thing. I want everyone to follow. So those who are grasping fastly, please cooperate. Those who are grasping slowly, try to understand my explanation clearly. Because I will not be with the same speed when we go ahead with the chapter. Fine. So let us start with the mathematical definition of mass. So how do we represent a mass in simple diagram is as a block. So with m as its mass. So then we write x of t. Okay, x of t, which is a basic symbol to represent displacement in mechanical or control system terminologies. So when do you expect a displacement? Obviously when you apply a force. Okay, force f of t. So now I can call force f of t as input and x of t, the displacement, as output. So there is a meaning for writing t inside bracket. Okay, when I say x of t, a displacement, it means it is a function of time, of course. And apart from that, it also represents instantaneous value of the displacement. So everything in real world is a function of time. Do you agree with this? Okay. So everything in this real world is a function of time. So writing x of t means displacement is a function of time. And writing f of t also means it is a function of time. Now you can ask me one question. X of t is not only function of time, sir, it is function of the input also. So it should be x of t comma f. X of t comma capital letter F inside the bracket. So I'm not telling that is wrong, that is also true. Okay, but most commonly it is understood and it is not explicitly mentioned to confuse the readers. Okay, so many textbooks write just x of t, or many papers, if you refer, just they write the function of time. But when there is an explicit definition required, okay, I mean, if you go for a complex system and there exist more than one inputs of different types, not only one type, different types, then we definitely write x of t comma something something, which is, okay, the displacement is dependent on. So for this simple definition, we will restrict our definition to x of t and f of t, which means they are of course function of time. And even if I don't write the t inside bracket, it is by default means it is function of time. I mean to say, even if I write just f and x, it means they are f of t and x of t without any doubt. Okay, so now look at into the left hand side and try to arrive with one equation for force and displacement. So we can use the basic physical laws to write a mathematical equation for the mass. But one thing is clear, we don't have some force equal to something in terms of x directly. The basic physical law explains force is equal to mass into acceleration. Okay, and the unit is Newton. So force is equal to mass into acceleration is the mathematical formula arrived by scientists. How they got this? That is left to you. You have to understand that part. I am going to use only for the application purpose that F is equal to m into A is the mathematical definition. So now moving ahead, we can write mass into acceleration as dv by dt. So dv by dt represents rate of change of velocity, which is nothing but acceleration. So F equal to ma into A is now rewritten as m into dv by dt, where v stands for the velocity in meters per second. Then again rewriting rewriting dv by dt as d by dt into dx by dt, where v stands for rate of change of displacement or distance. So v is rewritten as dx by dt, keeping d by dt outside the bracket. So now what will be the final expression? F is equal to m into d square x by dt square. Okay. So F is equal to m into d square x by dt square. So if you rewrite with a t term, okay, the function of time, the expression will just change to f of t equal to m into d square x by dt square. Fine. So this is the mathematical model of the mass. This is the mathematical model of the mass. Most of the students will get confused with the term t inside the bracket because it looks little complicated. I mean, those who are having difficulty in mathematics, understanding mathematical equations, don't feel it as difficult. What we are doing in the final step is just writing the parameter as a function of time. F of t equal to m d square x t by dt square is for mass. Okay, so now any 5 students can answer me. Is it clear or anything explanation is required? Any doubts? I'll give
Yes.
1 minute time. Different students can answer now.
Clear, sir.
I give option for all.
Fine, sir.
Okay, anybody else? Girls? I have not heard any
Yes.
voice from girls.
Yes, sir.
Yes, sir. Okay. No doubts, no clarification. Okay, I would like to clarify some more things. If everyone have understood, I'll not always teach the right thing. I intentionally make mistakes while writing. If you find out anything, you can tell. You are open to tell that. Okay. Okay, we'll move on to the next part now, which is spring. So here, okay, let me clarify again. F of t we call it as input and x of t we call it as output. X of t as output, or we can call it as effect, or we can call it as response. Fine. So next we'll move on to the other element, the mathematical definition of spring. So spring can be represented as shown. Okay. So one end is fixed and the other end is open. So the point A denotes free end and K represents the spring constant. K represents the spring constant. So now there is another diagram. Okay, before that, let us assume we have applied force to the spring. Somewhere, for now at free end we apply some force, F of t, and the other end is fixed. Since the other end is fixed to a rigid body, there will be a movement only at the free end. So we call it as x of t, the displacement at the free end. We call it as x of t. So now the other way of representing spring is with both as free ends. This is possible, right? So both cases are possible. Whether either both ends can be free or only one end can be free. You can ask, there can be both ends connected to rigid body. So please understand the meaning of rigid body. It means it will not allow any displacement. So if you fix both ends to a rigid body and apply force to the spring, it is as good as the dynamics of the springs are not changing at both ends. Okay, so which is meaningless. You cannot write a equation if there is no change in the dynamics at all. Fine. So that's what the meaning of these two diagram depicts. So both ends are free. Now let us see the second part. B is free end. This is also free end. A is also free end. So you can apply force to the spring anywhere. Okay. So we will have movement at the both sides, both x and xb. It is as good as holding a spring in both the hands. And you can apply force to the spring. The symbol of f of t, whatever I have written, okay, whatever the direction I have shown, it means it is not exactly that you are applying force here. This does not depict that you are applying force here. It just indicates some force is applied to spring. Okay, that's it. Don't make it complicated. So if you want to write mathematical equation for this, it is given as f is equal to k into x of t. That's it. Just like v equals to I into r. For a spring, the mathematical definition is f of t equal to k into x of t for this diagram. Okay. And for the other diagram, it can be written as f of t equals to k into xa of t. We have two displacements now, correct? So since we have two displacements, how we can represent this in a mathematical equation? We already know f is equal to k into x of t for a first diagram. But for second diagram, my question is, do we need to add the displacements at both ends, or do we need to subtract, or do we need to take the difference? What do you say? Think for a minute and tell me. Pawan Kumar Singh raised a hand. If you raise your hand, how to tackle it, I don't know as of now. You can unmute and ask directly. Pawan Kumar. Okay, anybody else?
That was our mistake, sir.
Okay, no problem. Anybody can answer this question? How do you represent the displacement part when both ends are free? Please try to imagine and answer. Imagine the practical scenario and try to answer this.
Sir, it may depend direction of displacement of both the ends.
It depends direction of the displacement at both the ends. Okay, of course. Then you can tell what are the different scenarios and how you can write the respective displacement factor.
If the displacement is in opposite directions,
Hmm.
and if
Okay, voice is getting stuck. I can't hear you. Sorry. No
Sir,
issue.
if the
Yeah.
displacement in the opposite sides, you should add those displacements.
Okay.
If the displacement is in only one side,
Hmm.
then you can subtract those, sir.
Okay. Okay, that's fine. Any other answers? Okay, that's it. I hope you have took time to think about this. So whatever you have answered is correct up to some extent, but as a convention, in theoretical studies, we always consider the relative displacement. The terminology is relative displacement. So when we say relative displacement, we represent that as a difference. Look at the symbol of difference. XA difference, XB. So what is meant by this difference is the relative displacement. In matter of the direction, we consider the relative displacement. So please understand this part. XA and XB, when both ends are free, we take the relative displacement into consideration to represent the spring in a mathematical equation. So when we encounter complex systems, then we will use the second expression. I hope it is clear. So remember the terminology relative displacement. Fine. So next, moving on to the third parameter, which is friction.
Excuse me,
Friction.
sir.
Somebody wants to ask any doubt? I can't hear you.
And that related displacement.
Sorry. Can you post a question if possible in the chat box?
Sir, can you explain that relative displacement once again?
Okay, relative displacement when two ends are free. Suppose imagine you are holding a spring in your hands, okay, right and left. Okay, so when you apply some force on this spring, which you are holding at both the hands, the right hand side will also get displaced, left hand side will also get displaced, and it can get displaced in any direction, either right or left. I mean to say, your right hand can move to right or left, and your left hand can move left or right. Okay, so under such scenarios, we cannot exactly define the equation for displacement for all scenarios. Okay, just for the purpose of understanding, we never define the displacement equation for all four scenarios, in theoretical studies at least. Instead, we define a terminology called relative displacement. So what matters for us is the relative displacement. Okay, so you may imagine, okay, sir, one is moving in this direction, other one is moving in the same direction. So if it moves right side, it is XA plus XB. If it moves left side, it is XA minus XB. If it moves this side, that side. So we are avoiding that complication just by defining a terminology called relative displacement.
Okay, sir.
Hmm. So any free end can move in any direction. Okay, I am telling only with respect to one dimensional. Everyone please understand this part also. When I am speaking only in one dimensional scenario. That is more key part. I don't know why I forgot to tell that. We are dealing here with one dimensional movement, 1D, 2D, 3D. I think you should be able to imagine if you have studied till then. Okay, so we are not writing any equation with respect to y. Please understand. One dimensional, only x. Okay, that's why it is relative displacement. Fine. I hope this much is sufficient for everyone. So let us move on to the damper part or the friction. This is how the symbol for the friction is written. Fine. So again, this damper friction, which looks like some piston kind of a thing. So let us write force input and x of t for the sake of symbolic representation. So here in this case, also we can have two scenarios where one end is free and the other case where both ends are free. And B represents the damping constant. Capital letter B represents the damping coefficient. So let us write f of t and xa of t for the second scenario, xp of t for the other free end. So just little bit to highlight on the 2D scenario, I mean two-dimensional scenario. When you try to arrive the equation for two-dimensional scenario also, which is quite complicated, you will end up, of course, with a y-axis coordinate also. y coordinate also along with x. So just think on that, how it might be, how the equation might look like. Will it be same as like a ya minus yb when both exist? Huh? When x and y both exist, will it be same as xa, xb, or will it be different, or will it be complicated to derive? Think on that just to ignite your thinking. Okay, we'll move on to this damper part now. Okay, how we write the equation for damper? Our frictional element is f of t equals to b into dx of t by dt. Fine. And when both ends are free, we write the relative displacement again at the position of x of t. So we replace x of t with the relative displacement xa of t and xb of t. Okay, don't call it as subtraction, addition, anything, just call it as relative displacement. Fine. So that's it for all the three elements. So if you are holding a pen and a paper, just write down for mass, it is f of t equal to m into d square xt by dt square. For spring, it is f of t equals to k into x of t. And just put a hyphen and mention when one end is rigid, one end is free. And the other equation for spring f of t equals to k into the relative displacement xa difference xb of t. And put a hyphen and tell when both ends are free. Similarly, for the damper, write down the final equation. Please write the symbol also, it's better. Then for the damper, f of t equal to b into dx by dt or b into d by dt. Again, the relative displacement xa minus, xa difference xb. Okay, so I suggest you to maintain notes. It will be easy to refer quickly whenever you want instead of moving the video forward, backward frequently. Okay, fine. Any doubts? I'll give 2 minutes for everyone to write it down. Meanwhile, if anybody has any doubts, any clarification, can ask. Please don't hesitate to ask any queries, any doubts. Feel yourself comfortable. Let it be silly doubt. Silly doubts you can ask in unit 1 itself instead of asking in unit 3, 4, 5. And don't hesitate to comment. Comment in the sense giving feedback about the teaching. You can give it directly. I will take it. I'll take it positively, but please understand my position also. I have to deal with 70 different heads, brains, which will have a different dynamics. Okay, so I have to tackle all the dynamics. So that's how I should prepare and explain. So that is the only constraint from my side. Other than that, nothing. Some may feel faster, some may feel easier, some may feel more explanation, some may even feel less explanation. So that's how we have to tackle. I hope it is clear for everyone. We'll move on to the next part. So these are three mechanical elements. The next part is transfer function. The next part is transfer function. What is transfer function? This is the very important, very important terminology of control system. Transfer function. Or somebody wants to speak? Okay. So next, what is transfer function? It can be defined as the ratio of output Laplace to the input Laplace. Okay, Laplace of input signal or input parameter to the Laplace of input signal or input parameter. This is the mathematical definition of transfer function. The actual definition is different. The actual definition is different and you cannot follow it if I tell it now, because it's something like you can understand only once you finish studying control system. So I just mentioned the actual definition of transfer function. A transfer function is defined as impulse response of the system. Okay, impulse signal, anyhow you have studied in signals and systems, you may follow it. The other definition for transfer function, I repeat, is the impulse response of the system. Impulse response of the system. If you follow it, that's great. Otherwise, let us wait and see what is meant by impulse response of the system. So to proceed with, if you consider a mass block, what was the input? Force was the input, and what was the output? Output was x of t So if you take Laplace of output and input, what we get is the ratio x of s by f of s. Let us see how do we write Laplace x of s by f of s. This is the transfer function for mechanical. What we got for electrical? For electrical, please understand, for a simple RLC circuit or any other circuit, we conveniently can assume voltage as the cause and current as the effect. So we call current as output because of the input voltage. Okay, but in different scenarios, the convention to define inputs and outputs will change. So what I mean to say is it is not always I of s by V of s in all scenarios. Sometimes you apply a current and you check what voltage you are getting across a resistance. So for you, current will be the input and voltage will be the output. So just for the sake of simplification or understanding, I'm telling, for a simple circuit, we can call current as the output, voltage as the input. So this is for mechanical system and this is for electrical system. So this is the definition of transfer function. So why Laplace? Why not with respect to time? Why it is not x of t by f of t? So all those questions will come into your mind. Okay. So all those questions can be answered once we actually go for a practical application, or one simple numerical can help you with that. Fine. Okay. So now assume, okay, consider one example and assume an RLC circuit like this. And let us apply an input of V of t and let the effect of voltage be represented in terms of current I of t. I of t as shown. So now for this circuit, I will tell V as input, I as output. So how we can write the transfer function for this? Okay, what is the transfer function for this? So just think on this. I'm not going to solve or write any equation, but I will give some things to think before solving. So please don't ignore those things. I want a parallel learning. There should be learning from your side also, and there should be a little teaching from my side. Okay, it's not a kid school to write everything and copy everything. That's how I go. But if you have any doubts, any clarification, without any hesitation, please post it. I welcome all kinds of doubts. And I think I have shared email ID to I have not shared for you. I have shared for other semester. You can note it down. guru@msrit.edu is my official email ID. And please post your queries. guru@msrit.edu. If you can post your doubts in that, it is fine. Otherwise, I will create a spreadsheet and share it to Ganesh. I have only his number. That's why I'm running behind him. I will create on spreadsheet and I will share it with you all. You can just type your queries there and it will keep updating. I will try to answer in the spreadsheet itself, or while giving the lecture also, I'll try to answer your queries if it is important. Okay, so this is just for the purpose of thinking what might be the transfer function of RLC circuit. So think on it, but we'll move on to the other example as of now. So I will try to get the transfer function of mass now. What I have drawn is not actual block diagram. It is a diagram for representation purpose. We have already seen how a block diagram looks like while studying the introductory part. So this is the equation of a mass, and we will apply Laplace transform for this. But key part here is we are ignoring initial conditions. Initial condition is very important. Many people will ignore it, but it is a very important part. But again, not to make any complications for the first step itself, I am ignoring initial conditions. It means there is no initial condition at all. There's no initial condition at all. Everything is starting from the beginning. Okay, what is initial condition? Some may not have understood even after entering fifth semester of electrical engineering. Just to give them some idea, I will explain what is initial condition. Okay. So let us take brain as an example. Brain as an example. When you get up in the morning, I will tell your brain's initial condition are 0. When you come to college, there will be some initial conditions in your class. After entering the class, the initial conditions will change. Everyone will start thinking your assignment, that, this. So your brain will start having so many things in your brain. Sorry, so many things of matters to thought about. So initial conditions will change. When sir enter the class, again the condition will keep on changing. Okay, for first class, different initial condition. After first class, during second class, while starting the second class, initial conditions will change. Okay, so initial conditions will keep on changing, but most of the times I assume initial conditions are 0 and start teaching. But you will have so many things in your head, writing records, assignments, all those things. So if I start teaching, assuming there is no initial condition, it won't be a good thing, no? I have to understand your conditions. I have to understand your conditions, and accordingly I have to teach. So what I will do, I will revise some things of the previous class and try to bring back you to the control system class. Then I will start teaching. So considering initial condition is good for both of us. If I ignore, it is bad for both of us. Similar to the practical world, in a control system also we will have the same thing. Okay, if you take a capacitor and if you directly keep it for charging, capacitor or one battery you can assume, if you directly keep it for charging without knowing its initial condition, it's not a good thing. Okay, or even if you make its analysis for some circuitry, you should always think of initial conditions in your equations. So that makes a better analysis. So that's it. So here we ignore initial condition for the sake of simplicity and we write the Laplace transform. We apply the Laplace transform. So things are very simple. F of s equals to m into s square x of s by dt square and all will disappear. I hope you are aware of this thing. So directly write x of s by f of s. Okay. So this is transfer function of mass block. Very, very simple. The simplest part, transfer function of mass. So next, coming back to the other scenario where we are not supposed to ignore the initial condition. With initial condition. Okay, with initial condition, what will happen if you apply the Laplace? Can anyone tell me? Do we need to add the initial condition? Do we need to subtract the initial condition and why? So can anyone answer me? I'll give 1 minute time. I request everyone to think at least. Okay, fine, that's fine. See, why I'm asking frequently you to think is I never teach from the perspective of exams. Please understand that part. And don't run behind me for important questions and all. The only thing is whatever I teach or you learn should be useful whenever you want to apply. That is the intention. So that's why I keep asking you to think and don't get bored, please. Okay. So we usually subtract the initial condition. We usually, not usually, we always. we have to. We have to subtract. So why we have to subtract? Why can't we add? So for that, another example I can give. If I tell you to, or if I ask you to check the amount of water or the level of water that has been changed in a glass after you fill it with certain amount of water. So my question is, what is the change in level of the water once you pour water in the glass? Okay, you say 10 centimeters of change. The size of the glass is 50 centimeter, but you say, okay, after I poured some water, there is a change of 10 centimeters. So when you say change of 10 centimeters, it's not from always 0 to 10. It can be from 20 to 30, 15 to 25, 17 to 27. Okay, why so? Why you told so is you considered the initial condition. The initial condition here is the level of the water which was already existing. So you obviously will subtract that. Okay. So you obviously will subtract. You will obviously subtract the initial condition. So if your final value of the level of the water is say 35 centimeter, then when you say 10 centimeter is the change, it means you have subtracted the initial condition, which is 25 centimeter. So that's why it is a subtraction. So I'll give clarification to everything, even if you know, just try to digest it. If you don't know, try to understand it. Fine. So this is how you can write. So now with initial condition, equation has changed slightly, it looks slightly, but when you write the transfer function for this, see, observe carefully. What we need is x of s by f of s. So when we need the transfer function, how it looks? Can we write x of s by f of s easily, so easily as that previous case? No, I'm stuck. No, I'm stuck. Oh, what to write? What to write? How do you write initial conditions here? Is it easy? No, it's not so easy. So now at this point of time, another question to think is, can we write initial conditions in the transfer function? Okay, the answer is in front of you only. Can we write it? Why can't we write? Ask yourself. Why can't we write? Why can't we represent initial conditions in the transfer function? Okay, fine. So, what's the time? Okay, 12:09. 1 more minute of time. So think on this. And meanwhile, look at the first transfer function, x of s by f of s equal to 1 divided by m into s square. So I hope you have solved the differential equations in mathematics. Solution of differential equations using Laplace method, so many other methods also. So my question is for today's class, I will answer in the next class. This f of t equal to m d square x by dt square is nothing but a differential equation. And if you want to solve this transfer function is of course one of the intermediate step. Okay, I mean the Laplace transform is one of the intermediate step, of course. So if you solve this differential equation using imagine Laplace method, then what you will end up with? What you will end up with, and what does that solution interprets? Okay, so that's a question for today's class. Think about it. And same for similarly, try to derive the transfer function for spring and damper. Anyhow, we'll do it in the next class. And try to understand the concepts. Try to understand the concepts. When I say understand concepts in the sense, by understanding concepts, you should be able to write or derive or arrive your own equations. Why concepts are always important is try to avoid remembering equations, understand concepts and put the equations by your own thought. So this is how the concepts are important. Please understand. Actually speaking, this one class is not sufficient to explain all these things, but little bit I have to take care of the syllabus also. So that's it. Thanks one and all. If any queries, I will share the spreadsheet immediately. We'll start a discussion forum in that. Thank you. Thank you one and everyone.
Thank you, sir.
Thank you, sir.
Thank you, sir.